Okay, so hello everyone, welcome to our the second seminar of the third season today. So our coming word today is the Maxim Dolgopolik from St. Petersburg. So he is a young young rising star mathematician who received the PhD and the diploma degree in applied mathematics and the PhD in discrete mathematics, both from the St. Petersburg State University. And in 2018, he was awarded the Young Mathematician Prize by the State St. Petersburg Mathematical Society. And now he has been working as a researcher at the laboratory control of complex systems. So today he's going to tell us about the DC semi-definite programming. So thank you for coming with us. So now the stage is yours.
Well, thank you for the introduction. So the topic of my talk is, as you said, DC semi-definite programming. The outline of my talk is as follows. At first, I will briefly recall some ideas from DC optimization, just to set up the stage for the rest of the talk. Then we will discuss two approaches to DC matrix valued functions and consider several examples of nonlinear semi-definite constraints appearing in applications and discuss how to compute their DC decompositions. Then we'll also consider DC structure of the maximal eigenvalue function, which is closely related to semi-definite programming problems. And finally, in the end of the talk, we'll consider extensions of optimality conditions and the so-called DC algorithm to the case of nonlinear semi-definite programming problems. So DC optimization, it's concerned with problems whose objective function and constraints can be represented as the difference of convex functions. So the main idea of the DC algorithm, which is probably the most famous algorithm from DC optimization, is to fix a point x0 and to choose a subgradient from the subdifferential of the function h with the concave part of our objective function. And then by the definition of subgradient, we have the following upper estimate of our objective function. It turns out that if x0 is a local minimizer of the function f, then it is a globally optimal solution of the corresponding convex problem, which is obtained by linearizing the concave part of our objective function. And this observation leads to the main idea of DC algorithm, which can be described as follows. You simply compute the subgradient as the current iterate and then solve the corresponding convex problem. And then move to the next one. Note that this method does not require line search as a use of trust regions to guarantee its global convergence, and it has many other useful properties. It works well both in smooth and non-smooth case, and it gained a lot of popularity in the optimization community. So this method can be easily extended to the case of constrained optimization problems. So if you have a constraint problem, then the same idea can be applied. You simply linearize the concave part of the objective function and the constraints, and then iteratively solve the corresponding convex problems to obtain the solution of the original problem. Here are some references that contain an overview of the DC optimization and DC algorithm, as well as detailed discussions of how this method was created, what are its applications, and many other things related to this method. I in particular will reference this paper by Lippe and Boyd a lot in my talk, because I based my research on DC semi-definite programming on the ideas presented in this paper. Lippe and Boyd discuss only heuristic ideas related to the method, while I tried to create a theoretical foundation for it. So next we move to DC matrix valued functions that arise in the context of nonlinear semidefinite programming problems. But at first, I would like to recall what nonlinear semidefinite programming problems are. They are usually formulated in the following way. So we have an objective function f, and we want to minimize it subject to this constraint. F of x, for each x, f of x is a symmetric matrix of a given order. And this relation simply means that for each x, the matrix f of x must be a negative semidefinite. This relation is called Loevner partial order, and it can be, as is written on the slide, described as follows. Matrix B is greater than or equal to matrix A if the matrix B minus A is positive semidefinite. Such problems arise in many applications, in optimal output feedback control, optimization of various structures, etc. And you can find these applications as well as a lot of examples in the wonderful PhD thesis by Michael Stingel, which is readily available online. You can search for it and you'll easily find it. There are a lot of important reference there. So this is, for me, this is a basic sort of reference when you want to know something about nonlinear semidefinite programming. So we would like to extend the ideas of DC optimization to the case of this kind of problems. But at first, we want to ask what do we understand by DC matrix valued functions f, like that. So since we have a partial order, we can consider natural extensions of a natural extension of the notion of convexity to the case of matrix valued function. You simply call function f convex if for all x1 and x2 and for all alpha between 0 and 1, the following generalized inequality in terms of the Loevner partial order holds true. And then we can call a function f DC if it can be represented as the difference of two convex in this order theoretic sense functions. While any such representation is called a DC decomposition of the function f. The definition is similarly simple, but it turns out that matrix convexity is a very tricky thing to do. And if you try to follow your intuition from the real valued case, then you are in a lot of trouble. So let's consider a simple example. We take this simple matrix valued functions, which maps each real x to this matrix, and let us check whether it's convex or not. So following the definition, we must take the right hand side of this inequality, subtract the left hand side, and check whether this matrix is positive semidefinite or not. So we take point 1, minus 1, subtract, and get this matrix, which is not positive semidefinite for any alpha between 0 and 1, and we can conclude that this similarly convex function is in fact non-convex in the order theoretic sense. Nevertheless, there are some similarities between DC matrix valued functions and DC real valued functions, and you can compute the DC decomposition as in a very similar manner. Namely, if you have a twice continuously differentiable matrix valued function f, and you know that the Hessians of each component of this function are bounded, then the function f is DC, and there is the following DC decompositions where mu must be greater than the estimate of the Hessian times the dimension of the matrix, which is very similar to the real valued case. Here you just must multiply by the dimension of the matrix. So how is this result proved? It turns out that, and it's very simple to prove, that a matrix valued function is convex if and only if the real function like that is convex for all z. And then applying the second derivative test to this function, you get this result. But we can also consider a different approach to matrix valued functions, namely component-wise. We call such functions f component-wise convex if each component of this function is convex. And similarly, we call such functions componentwise DC if they exist componentwise convex functions J and H such that F can be represented as a difference of such functions. And so now we would like to know, is there any connection between componentwise DC functions and DC functions in the order theoretic sense? As I mentioned earlier, you can consider these functions and check its convexity. If you put as vector z the canonical basis of Rn of the real space, then you get that diagonal elements of a convex matrix valued function f must be convex. But what about non-diagonal elements? And it turns out that they can be non-convex. So let's consider this example. So we have the function f of x, and we have non-convex functions as its diagonal elements. We form this quadratic, this function, and then apply second derivative tests, and it turns out that for all that, this function is convex, and therefore this matrix value function is convex in the order theoretic sense. So we can conclude that non-diagonal elements can be non-convex, but how non-convex can they be? Can they be discontinuous, or they must be continuous? So we would like to know that, and it turns out that they have an important property, namely, if you have a convex matrix valued function f, then all its non-diagonal elements are DC functions. Let me outline the proof of this result and the idea of it in the two-dimensional case. If you put as that vector whose all coordinates are 1, then you know that this function is convex. Then rearranging the terms, that you get that the non-diagonal elements can be expressed as the difference of this convex function and then diagonal elements which we know are convex, and therefore non-diagonal elements are DC. In the case of general L, this result is proved by induction in L. As an important corollary to this result, we first get that if a matrix valued function is convex, then it must be Lipschitz continuous on bounded sets. Then we have that convex matrix valued functions are in fact twice differentiable almost everywhere, which is a nice property. And then we can also have this very important corollary that any DC matrix valued function is in fact componentwise DC. The question is whether the converse implication holds true, and to be honest, I don't know, and it's very difficult to tell at the moment. So it's a challenging open problem to prove whether componentwise DC functions are in fact DC in the order theoretic sense or not. So let's consider several examples of nonlinear matrix valued functions appearing in applications. A common example is quadratic or bilinear constraints, which have form 1, or a particular case is functions depending on two variables x and y, which have this form. Such functions appear in various control problems, such as simultaneous stabilizations of single input, single outputs, linear systems by one fixed controller of a given order, and many other applications. And you can find particular examples in the Stingel's PhD thesis, which I mentioned earlier. So how do we compute DC decompositions in the order theoretic sense of such functions? Using the theorem about twice differentiable functions, we can define mu greater than this value, which is defined by the quadratic part of our function. And you have a DC decomposition of this simple form. Now that if you want to compute component-wise DC decomposition, you would have to compute such L squared DC decompositions of real valued functions, while here you just need to compute this value, and then you get the desired DC decomposition. Also, a different DC decomposition of this function can be computed, namely if you form this huge block matrix whose elements are matrices that define our function. And then if you can compute its decomposition to a positive definite and negative semi-definite parts, then the C decomposition can be defined via these positive and negative semi-definite parts of our block matrix A. And such decomposition can be used whenever matrix A has a simple structure, such as only when its diagonal elements are non-zero. So next is another example. Such constraints appear in optimal H2H infinitely static output feedback problems. And once again, we can apply our theorem and compute the value M, which is computed in a slightly more complicated way here, while the matrices B and C, which make our constraint non-convex. And then with the use of the theorem, we get the following DC decomposition of our nonlinear function f. And finally, a third example, it's called the so-called Stiefel manifold or orthogonality constraint, which appear, for instance, in multi-matrix principal component analysis. And following the idea of Lipp and Boyd from the aforementioned paper, we can rewrite it as two inequality constraints of this form. And it's easy to check that matrix, the function G is in fact convex while H is concave. Well, one can object that it's degenerate to rewrite an inequality constraint into two inequality constraints. However, DC programming methodology is very robust and is demonstrated by numerical examples from this paper by Lipp and Boyd. Such reduction of these equality constraints into two DC inequality constraints works well in practical applications. So now we have two approaches in our hands, so the theoretic and component-wise, and we need to know how to apply them to solve nonlinear semi-definite programming problems. At first, we start with component-wise approach, and here we must consider the maximal eigenvalue function, because if you have a nonlinear semi-definite programming problem of the standard form, you can rewrite it as an inequality constraint problem involving the maximal eigenvalue of the function f. So we want to know if the function f is component-wise DC. Does the maximal eigenvalue function does it have a DC structure or not? And it turns out it has. So if our matrix valued function f is component-wise DC, and we know DC decompositions of its elements, then you can compute DC decomposition of the maximal eigenvalue function, which is defined as follows via the elements of the function h. Here we have this a little bit scary maximum, but in fact you don't need to compute it, because at first you know that to compute the value g of h x, you simply need to add the maximal eigenvalue to the function h, which is defined simply as the sum of the elements, while its subdifferential can be computed via the eigenvectors corresponding to the maximal eigenvalue. And so, knowing the DC decomposition, we can apply DC optimization methods to the reformulation of nonlinear semi-definite programming problems in terms of the maximal eigenvalue function. But what to do in the case when the function is DC in the order theoretic sense? To answer this question, we need to consider optimality conditions for such problems. But we will consider more general problem, namely we will not restrain our consideration to semi-definite programming problems, but we'll consider more general constraint problems of the given form. So here f0 is DC function, and this inequality is defined via proper con k in a Banach space Y. And the partial order is defined in a standard manner where the cone is meaning that y is greater than or equal to x with respect to this order if y minus x belongs to the cone k. And the function f is assumed to be dc with respect to this partial order in the same sense as above, meaning that the following generalized inequality with respect to the cone k holds true for both j and h. G and H. If the space Y is the space of symmetric matrices of a given order, and the cone K is the cone of positive semidefinite matrices, then you get nonlinear semidefinite programming problems. However, you can also consider K as a cone of as a Lorentz cone or second order cone, and you get a nonlinear second order cone programming problems. And you can also consider semi-infinite programming problems as a particular case of this problem. And we would like to define obtain optimality conditions for this problem and extend DC algorithm to the case of this problem. So for the sake of simplicity, we will suppose that the concave part of our constraint is differentiable. And it turns out that the same optimality conditions as in the real valued case hold true in this more general setting. Namely, if you fix a subgradient of the concave part of the objective function, then for x star to be a locally optimal solution of the problem P, it is necessary that x star is a globally optimal solution of the corresponding convex problem, which is obtained by linearizing concave parts of the objective function and constraints. How are these optimality conditions related to more standard optimality conditions such as KKT conditions? And it turns out that they are related in the following way, namely if this constraint qualification holds true, which is very similar to Robinson's constraint qualifications, and the optimality conditions from the previous theorem are in fact equivalent to the KKT optimality conditions. They are just written in the form that is more convenient for our purposes. And I forgot to tell you that points x for which satisfies the optimality conditions are called critical for the original problem. And the goal of DC optimization in a local sense is to find critical point of such optimization problems. And now we can turn to the extensions of the DC algorithm to the case of cone-constrained optimization problems defined above. Namely, we know that if a given point is non-optimal, then by solving the corresponding convex problem obtained by linearizing our original problem, we can find a better point with a smaller value of the objective function. This convex problem is constrained, but many methods can be applied to solve it, such as interior point methods and augmented Lagrangian methods. And you can consult the paper of Leap and Boyd, where they discuss how this problem can be solved. And if we found the solution x1 of this problem, then it turns out that the value of the objective function at this point is necessarily smaller than the value of the objective function at the initial point x0. And furthermore, x1, if x0 is feasible for the original problem, then x1 will also be a feasible point of the original problem. So using this property, we can define a natural extension of the DC algorithm to the case of constrained optimization problems as follows. We simply compute a subgradient of the function h0, then the derivative of the concave part of the constraints, and then solve the corresponding convex problem obtained by linearizing our problem at the current iterate. And then repeat this process. But it's important that this method would work only if a feasible initial point is known. If such point is unknown, then the feasible region of this convex problem might be empty and the iterations are not correctly defined. We can prove the following theorem about the convergence of this method. So if the objective function is bounded below, then first the sequence constructed by the method is feasible for the problem P. If the iterate is xn is not critical, then we have this strict inequality. So the value of the objective function strictly decreases along iterations. While if xn is critical for the problem P, then the process terminates. And if it doesn't terminate, then the sequence of values of the objective functions converge to a certain value. Then if the concave part of the objective function h0 is strongly convex, then we have the following estimate of the decay of the objective function, which can be used as a basis for the stopping criteria for the method. Namely, you can terminate the method if the difference between two consecutive iterates is smaller than given value, or if the difference between the values of the objective function is smaller than the given value. And finally, if the sequence converges to a point x star in which this constraint qualification that was used in the optimality conditions is satisfied, then this limit point is necessarily critical for the problem P. However, as I mentioned earlier, there is a drawback to this method because you need to know a feasible starting point, and if you don't know, then you're in trouble. And so we need to extend this method somehow to the case of when we can't compute a feasible starting point, and it can be done following once again the ideas of Lipp and Boyd with the use of the penalty technique. Here, I would like you to look at this modified convex problem, and I'll try to explain how this problem is obtained. Basically, what you do is you relax the constraint. If you consider one-dimensional case, you simply add a positive non-negative number s to the right-hand side and relax the constraint. But in order to make a certain sense of this relaxation, you need to penalize it, and you add this penalty term to the objective function of the convex problem. And the iterations of this method go as follows. You compute, as usual, the subgradient, the derivative, and you solve this penalized convex problem. But then, since it's a penalty method, we must define penalty updating rule, because if the penalty parameter Tn is too small, then the method wouldn't work properly. And here I described only the simplest penalty updating strategy, but in practice, one can and should use more elaborate penalty updating strategies, which I do not discuss here simply, well, for the sake of simplicity of the exposition. Just a few more comments about the penalized problem that appears here on the step 3 of the method. If you have an inequality constrained optimization problem, which is DC, then the corresponding penalized problem can be written in the following way. You can resolve it with respect to S and obtain simply the penalty subproblem, which can be viewed as an application of the DC algorithm to the weighted L1 penalty functions phi t. Here you can have a direct connection between standard penalty methods and DC algorithms. However, in the general case, when the K is non-polyhedral, there is no such straightforward connection, and you can rewrite its iterations in terms of a certain penalty function. However, it does not have a simple analytic expression. At first, we would like to know when the iterations of this penalty method are correctly defined. And it turns out that if the space Y is finite dimensional, the current K is generating, and the corresponding penalty function defined via this in the standard way by the distant function is coercive, then the iterations of the method are correctly defined, provided the initial value of the penalty parameter is sufficiently large. Then we know that this algorithm converges to critical points of the original problem, but here it might converge to infeasible points, and we must extend the idea of the critical point to the case of infeasible points. And it can be done in the following way, namely a point x star is said to be generalized critical point if there exists subgradient of the function h0 and a certain vector s0 such that the corresponding pair x star s star is a globally optimal solution of the corresponding penalized problem. This is a complicated definition, but in many particular cases it can be written in the simpler terms. In particular, for inequality constraint problems, a point x star is a generalized critical point if and only if it's a stationary point of the corresponding penalty functions, which can be written in terms of the Dini subdifferential of this function. And then we have this important property of the method. So this in the case of the DC algorithm, we had that we showed that the values of the objective function are non-increasing along iterations, but here this property is no longer true, and you must correct the value of the objective function by this additional penalty term, and to ensure that this value decays. And if so, having this property, having this inequality, we can define the natural stopping criteria for the method as follows. We can consider the difference of these values and the norm of Sn, which can be viewed as an infeasibility measure for the current iteration. And so finally, two convergence results for the penalty version of the method. First of all, under certain technical assumptions, all limit points of the sequence generated by this method are generalized critical points of the problem, which might be infeasible, unfortunately. But if the sequence converge to a point satisfying the constraint qualification, which we discussed several times earlier, then necessarily the limit point is a critical point, and furthermore, the iterations eventually become feasible for the problem under consideration. And so that's mostly all I wanted to say. Thank you for your attention, and if you have any questions, I would like to answer them.
Okay, thank you, Maxim, for your interesting talk. Is there any questions to our speaker from the audience? Okay, Bruno has a question, so you can directly ask Maxim. Oh, Bruno.
Can you hear me?
Yep.
Okay. First, thank you very much for your talk. It was very interesting. I really like cones, and so yeah, I was very happy to see that there was a final discussion at the end about very general situations. So that was actually what I wanted to ask. So in the first part of your talk, you have some decomposition results that were very specific to the semi-definite programming case. I was just curious the extent to which they can be generalized to the general conic setting. So for example, I think you have some result that if the Hessian, so if you know some bounds to the Hessian, then you can use this to get a DC decomposition, right?
Yes.
Yeah, I suppose that if you have a general cone and you substitute the identity matrix by a relative interior point in the cone, might be able to do something similar in general as well.
Yes, I suppose it's possible, and it would be interesting to check it.
I'm just guessing. I'm not saying it's definitely possible, but Yeah, I suppose that some of these things, yeah, so I'm curious to know the extent to which, some of these things have you been investigated in general setting for
Well, I have not investigated them in the general setting yet, but I would like to. So thank you for your comments. I agree that it seems possible to extend this result to a more general setting.
Okay, thank you. I think I'm very sorry. I think I still have one more extra question. So in the case of nonlinear semi-definite programming, it is known that when you take a look at the second order optimality conditions, some special terms appear. So these are the so-called sigma terms.
Yes.
And then I was just curious if this decomposition leads to any insight on the second order optimality conditions of the, because I saw that you gave the first order analysis, kind of first order analysis of the optimality conditions, right?
Yes, I considered only first order analysis, and to be honest, I don't know what would happen in the second order case.
Oh, okay, thank you. I think that was all I wanted to ask. Thank you very much for your talk. It was very interesting.
Thank you.
Yeah, thanks, Bruno. And any other questions? You can just write on the chat as well.
I have not too interesting questions. I would like to know what the PhD thesis was you mentioned, because I forgot to take notes. And
Okay.
and I also wanted to know whether you could explain a bit what this constraint qualification actually means. So
Yes.
Michael Stingle on the solution. Okay, thanks. And yeah, if you could explain a little bit what this constraint qualification means, that would be.
Yes, yes. I just a second. Well, if the cone K has non-empty interior, then it's simply a Slater condition for the corresponding convex problem. While if the cone K has empty interior, then it's sort of a Slater condition as well, but just in this generalized form.
Yeah, is that possible to see that somehow? And because I somehow don't.
Yes, there is a book by Bonas and Shapiro, Perturbation Analysis Optimization Problems, and they prove this. Well, essentially, very similar result there. I can, in fact, well, they discuss Robinson constraint qualification and its relation to Slater condition, and you can find it in this book by Bonans and Shapiro, Perturbation Analysis of Optimization Problems.
Okay, so it's basically a modification of a standard perturbation result.
Yes.
Okay, yeah, thanks.
Yeah, so we have another question in the chat from I guess from Dixon, that is there a class of problems for which the sequence xn converges of 10 to infinity?
I'm sorry.
There is in the chat, so I mean.
Yes, I see it. Well, yes, it can converge to infinity, and to guarantee that it doesn't, we must impose certain coercivity conditions. So suppose that certain sublevel sets of penalty functions involved in this problems are bounded. But in theory, you can define such problem and such choice of find such choice of initial parameters that the iterations probably, although I'm not sure, but it might be possible, I think.
Sorry. Can you present the theorem 5? Not this. After this.
Which
Theorem
one?
5. Theorem 5. But not this. Not this slide.
Just a second. Which one? 6?
Yes, maybe.
This one, yeah.
Yes. So in the item 2, so the sequence F0 Sn converse. So it's maybe this converse, but not optimal value, right?
Yeah, yes, it might converge to simply critical value. It does not have to be optimal.
Yeah. How about if, for example, the data is polynomials? So as far as I know, in the case of analytic function, the gradient method, the gradient method. So the sequence is bounded or tend to infinity. Only 2 cases in gradient method, right?
Yes.
So I would like to know in this case, yeah, for example, if F0 and capital F is polynomials, so the sequence is bounded or tend to infinity, the same.
Unfortunately, I don't know. I can't answer right away.
Yeah.
So is that what you meant by if x and it converges to infinity, mean that the norm converges to infinity?
Yes.
Yeah. So which means that it diverges, the sequence diverged. I mean, converts to infinity, the norm converting unbounded. And then what can you say about that situation?
Well, if the problem has an unbounded feasible region, then I guess it's possible that the sequence would diverge, but nothing really can be said about the behavior of the method in this case. To prove any results about its convergence, we must assume that the feasible region is bounded, or that the objective function is coercive from the feasible region. Otherwise, my convergence analysis fails.
Yeah, thank you.
Okay, thank you. Do you have any other questions? Yeah, we have another.
I'd like to.
Bruno. Oh yeah, Judge as well. Okay, I think Judge is first, and then Bruno. Yeah.
Please go ahead first. I already asked my question.
No, that's okay. It's okay.
Yeah, we have plenty of time, so don't worry.
Okay, sorry then. Sorry, one thing I forgot to ask is, so do you expect, so suppose, for example, that you have a nonlinear SDP, and then, of course, for example, you can do this decomposition. But do you have, did you do some numerical example, for example, that shows very clearly that you indeed get some numerical advantage by solving? Because if you do this DC decomposition, you still need to solve nonlinear but convex SDPs at each step. But for example, the guy who wrote that thesis you mentioned, so he is one of the developers of VAOpt, right? Something.
Yes.
And so if the functions are differentiable, you could still try to solve it in one shot directly as a nonlinear STP, for example, with their method, right?
Right, you're correct.
So
I guess I understand your question. The thing is that, yes, this method reduces a nonlinear problem to another nonlinear problem, which the only benefit of it is that the second nonlinear problem is convex, and it might be hard to solve. And the method would work well only if the convex problem is simpler than the original nonlinear one. I have not done any numerical experiments yet to confirm that this approach is better in some cases, but there are some examples in the paper by Leap and Boyd, which I mentioned several times. Just a second. They have example of nonlinear semi-definite programming problem, and they apply this method, and they report a very promising results of numerical experiments. I haven't computed anything yet, but I hope to test this method on various applications in the future. The first step was just to present theoretical analysis, and then I would like to move to applications.
Ah, I see. Thank you. Yeah, that was it. Thank you very much.
Yeah.
Would you be able to tell more about the selection of the penalty parameters or the updates of the penalty parameters? Because you said that it was a little bit long to dwell into.
Well, yes. Just a second. Here I presented only the simplest rule. So when basically here it says that if the point is infeasible, you increase the penalty parameter until we reach the pre-specified maximal value, and if the point is feasible, we don't, which is a naive strategy, and it shouldn't be used in any real computations. The thing is, it depends on what kind of problem you have. If you can solve this problem with linear objectives, then the so-called steering penalty rules can be applied to estimate the penalty parameter. If you can't, it's possible to use some estimates via, if you can solve this problem efficiently and find the corresponding Lagrange multiplier, then you can use this Lagrange multiplier to improve the current value of the penalty parameter, and you this strategy in the case of inequality constraint problems is given in the original description of the DCA2 algorithm, which is again mentioned in the paper by Leap and Boyd.
Mm-hmm.
So in general, it's very difficult to recommend any particular penalty updating strategy. If you can solve the problem with linear objectives, then it's recommended to use steering penalty rules, which are based on solving the feasibility problem first, then using the obtained result to decide whether you need to increase penalty parameter or not.
So one can consider some kind of duality scheme to treat the penalty parameter as a dual variable?
Yes.
Would that
Not
be a
exactly
possibility
like-
here in this setting?
I don't really know, but I think it should be. I haven't considered it yet. But in the case of inequality constraint problems, it is possible.
Okay, thank you.
Thank you. So is there any other questions? Because we still have 5 minutes for 1 or 2 questions. So at the meeting,
if there are still some minutes, so may I ask a question? So first of all, Maxim, thank you so much for your presentation. It was really very, very interesting and very detailed. So I just was wondering, so people who work in DC, do you know if there is some hope for difference of quasi-convex functions? So these functions, they do get quite a few properties from convex functions, but not all of them. So is there any hope here to get some reasonable computational methods? So do you know?
Unfortunately, I don't know.
I have a question on top of Nadia questions, because I think in your theorem 5 that I think the reason why it converges because every step you make sure that the value of the function decrease, right? I mean, strictly
Yes.
decrease. So that may be possible if the function f is quasi-convex, isn't it?
I guess probably.
Yeah, because not just quasi, but like so do convex something, but yeah, because if you find a descent direction and then you go to that direction, then the value of the function decrease. So I think that may be possible. I don't know, just my observation.
Well, here the thing is that in the DC algorithm you do not look for directions and you don't solve line search problems. Maybe some modifications can be made to make it possible to apply such methods to quasi-convex problems.
I see. And another question, I'm sorry, another question is that based on this, like Zachin asked about using dual problem to update the penalty. Is there any dual problem yet for this kind of optimization? This class of optimization? Yeah.
Yes, of course you can write the dual problem for this convex problem and compute corresponding dual variables and use them to estimate the penalty parameter. However, it's unclear whether it would be useful in this setting because the problem is already very difficult and I don't know.
Then I have a conceptual question. I mean, if you are solving one convex problem after another, but
yes,
the constraint that you're trying to get right, and where you are basically where you have some stack that is the concave part, right? So how
yes.
does the Lagrange multiplier of the convex part of the auxiliary problem help you to get step size control that actually has to get the concave part of the constraint right?
Well, it's the thing is that it can be used only as a low estimate of the penalty parameter. If you solve this convex problem, found the Lagrange multiplier for the convex problem, and suppose that it's much great, its norm is much greater than the norm of the penalty parameters that you're using, then there is definitely something wrong and you must increase the penalty parameter. The idea is like that. You cannot use it to, but if the penalty parameter is greater than the norm of the multiplier, you can't really say whether you're doing things right or not. And as I mentioned earlier, steering rules seem to be more promising when you solve feasibility problem first to estimate the optimal value of this parameter as here, and then you decide whether it's decreasing fast enough with iterations or not, to decide whether you increase the penalty parameter or not. But this approach is applicable only when you can efficiently solve the feasibility problem.
Okay. Yeah, I think you told me as much as I can absorb. Thanks.
Okay, thank you. Is there any other questions? We have 3 minutes left. So we have time for a very quick question. Okay. So if we don't have any question left, so please join me to thank our speaker for his interesting talk. Yeah, and
thank you, Maxim. Very nice presentation.
Thank you very much, Maxim.
Good slide.
Thank you for having me.
Perfect time.
Thank you, Maxim. Thank you.
Very good
Thank you.
language.
Thank you.
Yes, great talk. Thank you.
so we will have, yeah, so we have seminar next week. So if you have time, then just join us next week. And so thank you everyone, and see you all next week. Bye.
Bye.
Thanks,
Bye.
Không thôi.